Machine learning and artificial intelligence have become the latest buzzwords within our industry, and they continue to increase in popularity year on year. According to Google Scholar in 2020, there have been around 1,100 papers published for machine learning in petrophysics, and we're already close to that for 2021 so far. So, is machine learning and artificial intelligence just buzzwords, or do they have real applications in helping improve our well-established petrophysical workflows and understanding well log data better? I'm Andy MacDonald, and in this presentation I am going to cover a number of applications where machine learning can be used to enhance and improve the petrophysical workflow. But first, we need to cover what machine learning actually is. Machine learning is a branch of artificial intelligence and computer science that focuses on using data and algorithms to imitate the way that humans learn. And the definition used here is a simple one that I've come across, and it is the ability for machines to learn from data without being explicitly programmed to do so. This means we initially train models to start with, and anytime new data is presented to the model, it should be able to handle that data and apply the model to it to get the desired results. In other words, the algorithm or model should be able to generalize to new data. Where does machine learning fit in? First, we have to discuss artificial intelligence, or AI, which is a vast discipline that covers computer vision, robotics, expert systems, speech processing, and machine learning, as well as many other related subdivisions. According to the former Dean of the School of Computer Science at Carnegie Mellon University, artificial intelligence is the science and engineering of making computers behave in ways that until recently we thought required human intelligence. We then have machine learning, and a further subdivision of machine learning is deep learning. This focuses on the use of deep or multi-layered neural networks to gain deeper insights into our data. Another term you may have heard of in recent years is big data, and this refers to the large volumes of data that is generated by humans, machines, and tools that is often too large or complex to be processed using traditional computing technologies. Instead, it requires new and innovative technologies to gather, manage, and process that data. Big data can feed into AI, machine learning, and deep learning to provide a greater understanding of our data. How does machine learning compare to traditional programming? In traditional programming, we create a model or a set of instructions, typically based on if-then-else logic, and then we apply it to the data to get our required results or answers. But due to the complexity of data and its variation, conventional programming may not be suitable for our needs. Machine learning, on the other hand, is where we provide the data alongside the answers, and these are then used by the machine learning algorithm to derive the final model or set of rules, which can then be applied to new data to make predictions. To illustrate how popular machine learning is becoming within the petrophysics domain, multiple searches were carried out on Google Scholar for the term petrophysics and machine learning since 2010. As you can see, we start off with relatively few publications until around 2015, where we start to see a more marked increase in the number of publications. In 2020, there were around 1,150 publications. And in this year alone, we are already at 1,100 publications, and we're close to that, and we will likely overtake it. It may seem that machine learning is a relatively new concept to us, but many of the techniques date back many decades, with the first ideas of neural networks being discussed in the 1940s. It was only when computing power increased significantly in the 80s and 90s that many of the theories that underpin machine learning today could be realised. Also, machine learning back then may have been known as statistics, mathematics, and statistical inference. There are a few different types of machine learning: supervised, unsupervised, and reinforcement learning. Supervised learning is the most common and practical of machine learning tasks. It is designed to learn from example or labeled data. It uses input data that has been paired with the correct outputs. After training of a model, it can be used to predict new outputs based on the inputs. And examples of this within petrophysics can include Facies prediction as well as permeability prediction. Unsupervised learning, on the other hand, is used to identify underlying patterns and relationships in the data without the need for labels. And these methods focus on the data rather than the labels. As there is a lack of labeled data, it can often be difficult to validate and verify the results. In petrophysics, unsupervised learning can be used for Facies prediction and outlier detection. Reinforcement learning is goal-orientated. It learns to make decisions in order to achieve complex objectives based on interactions with its environment without the need for supervision. The algorithms seek to cumulatively maximize their reward each iteration by using experience from the past iterations. So let's have a closer look at supervised and unsupervised learning. Supervised learning can be further broken down into regression and classification-based tasks. Regression-based tasks allow us to predict continuous and variable numeric outputs. They take the input data and map it to an output. Examples include permeability prediction and synthetic shear prediction. Classification tasks allow us to predict a discrete output. They take the input data and map it to a discrete output category. And an example of this is Facies prediction. Unsupervised learning includes classification and also dimensionality reduction. Classification and unsupervised learning identifies patterns within the data without any labels. They look for clusters of data and group them together, and this can be done using methods such as k-means clustering and k-nearest neighbours. And examples include automatic outlier detection as well as Facies classification. Dimensionality reduction takes multiple inputs and reduces them to a more meaningful number of inputs. For example, we may have 100 inputs, which can be reduced to 20 that contain the most important information. So let's now have a look at where machine learning can be applied in petrophysics. You may be thinking that machine learning can be used to directly predict key reservoir properties and bypass the traditional methods that we are used to. And you're correct, this is one of the applications, but it can also be used in a number of other areas in the petrophysical workflow, especially during the data QC and preparation stages. It is this stage that can take up a significant amount of time during a project. In some instances, it can be up to 90% of the available time. Machine learning can be used to identify and repair bad data that may have been impacted by poor borehole conditions, fill in missing data or create synthetic curves, normalize our data, and make predictions such as Facies curves and continuous permeability from discretely sampled core data. It can also be used to automate the well log correlation and depth shifting processes. This is only a small selection of where it can be applied, and there are many other areas being discussed in the literature. So the first application we will look at is outlier detection or bad data detection. We can use this as an initial exploratory step to identify where we may have data points that are anomalous, and these are also known as outliers. Outliers are points of data that sit outside the normal or expected distribution of the data set. Outliers can occur for a number of reasons within well log data, including measurement errors, tool and sensor problems, unexpected events or unexpected geology, and changes in the borehole environment. We can use unsupervised machine learning methods to identify these outliers, where all the user has to do is provide a level of contamination. Or we can use supervised methods, where the model can be trained on existing data where bad data has been manually flagged by an interpreter. In this example, we have two different unsupervised methods for identifying outliers. On the left, we have k-nearest neighbours, and on the right is angular-based outlier detection. The k&n method considers the Euclidean distances between the data points. If points are close together with multiple neighbours, those points could be considered similar. In cases where fewer points or singular points are further away from the main group of data points, they can be considered outliers. In ABOD, angular-based outlier detection, the variance of the angles between the point and other points within the dataset is considered. If a point is an outlier, it will reside further away in space from the other data points and therefore have a small variation in angles to its nearest neighbours. If the point is among other points, the angles between the nearest neighbour vary greatly. And this method is suitable for datasets of high dimensionality and provides a more robust and stable measure of outlierness. So once outliers or bad data points have been identified, it is possible to repair the data using machine learning. To achieve this, we would select data that is considered good from the same well and the same formation, or from multiple wells in the same formation. We then use this data to train our machine learning model and then predict our target output. Once we have our final curve, we can compare the prediction with the true curve in areas where it is considered good, and from this we will be able to tell how well the model has performed. If we are happy with the model result, we would then splice it in over the affected intervals, like in this example here. In this situation, multiple linear regression was used to repair a bulk density measurement, and the results were then spliced in to form the final curve, which is indicated in black and overlies the red curve when in the good interval, but then overlies the dashed black curve in the interval that has been repaired. While log normalisation commonly forms part of our petrophysical workflow, however, there are a number of petrophysicists who prefer not to apply it, as if used blindly and incorrectly, there is a potential for removal of key and important geological features. Therefore, it is important to QC the results with your geologist or stratigrapher to ensure that nothing has been removed accidentally. So why do we want to apply normalisation? It is commonly assumed that stratigraphic units within neighbouring wells should share similar properties, and therefore they should have similar log responses. If there are discrepancies even after applying borehole corrections, there could be other factors at work, such as differences in tool and sensor technology, or differences in the borehole mud system. Ensuring that data is accurate is key for field-wide and regional studies, and it is also good for carrying out effective machine learning. Additionally, normalisation can make it easy to compare data between multiple wells and also carry out effective batch processing using similar interpretation parameters. Traditionally, normalisation is carried out on gamma ray logs, but it can be carried out on other logs as well. It is done first by selecting a key well, and then adjusting all other wells to that well. An example of this is seen here in the histogram. At the top, we have a number of wells through the same interval before normalisation, and then after normalisation on the bottom. And you can see that the curves, or the gamma ray curves, are in agreement in the bottom one after normalisation. Ackert et al. Recently applied machine learning to this problem, where they had a reference formation and a well picked by the geologist, which can be a subjective process in itself. This tight limestone unit, Zone B, was expected to have the same response over the area of interest, and we can see here the results of their research, with the original logs showing a slight separation between the density and neutron curves. And then after the machine learning normalisation, we can see that these are overlying, as we would normally expect within a tight limestone. Another application of machine learning is within missing data prediction. It is essential that datasets are as complete as possible when carrying out subsurface characterization. However, there are situations where well logging measurements are missing, and reasons for this can include different vintages of well logs, logging speeds exceeding tool sampling rates, borehole environmental issues, improper data management, and expensive acquisition costs. There are a number of ways in which this missing data can be handled, and traditionally we have used empirically derived relationships to create synthetic curves such as acoustic shear slowness, using the Castagna-Greenberg relationships, and also VP-VS ratios. We are also familiar with the creation of synthetic permeability curves using equations such as the Temer equation, which calculates a permeability based on other logging measurements without the need for core samples. More recently, machine learning algorithms have been used to complete the well log set by directly predicting the missing curves. Models are trained and tested on offset wells where the target data is present, and it is then used to predict the missing data affected in the wells. It should be noted, however, that infilling data should be done with caution, as it can often skew the results and introduce bias into the data. Therefore, it is essential this process is not carried out blindly, and the results should always be checked afterwards by the petrophysicist. In this example here, the authors have attempted to predict photoelectric factor in multiple wells, and we can see here that there is reasonably good agreement between all of the test wells. The blue is the actual PE and the red is the predicted PE. There are some variations which could be improved by improving the machine learning model or supplying additional training data, but overall is a very good match. Another area where machine learning has been able to help within petrophysics is in well correlation and depth matching. Depth matching and well correlation can be time-consuming tasks and requires domain expert knowledge to ensure that the correct matches have been found. Additionally, when carrying this out, bias may be introduced unknowingly by the interpreter, as it is down to their subjective interpretation of the data. The authors here have used a deep convolutional neural network to carry out pattern matching using a number of seed wells, which have been interpreted by an expert and had the geological complexity included in the model. This allows the process to be carried out much more quickly and with greater accuracy. Depth is a critical measurement for the successful development of an asset or a well, as it allows for the appropriate selection of casing depths, perforation intervals, and setting of packers. The process of depth matching is normally carried out by the petrophysicist and can be time-consuming, tedious, and a subjective task. What one petrophysicist may pick for matching the logs may differ from that of another petrophysicist, and this is where machine learning can come in and speed up the process and maintain consistency. This example here from Wang et al. In 2020 illustrates the use of a deep neural network to carry out pattern recognition and depth matching. They utilise a sliding window with a fixed length on both the reference data and the target data. The deep neural network controls how much to move the sliding window until a best match is found. The authors found this to be an effective solution for depth matching and reducing the amount of time spent on this task whilst maintaining a consistent approach. So one of the key deliverables from a petrophysicist is permeability. Permeability is used to provide an indication of how easy fluids flow through a rock or a reservoir. At present, there is no logging tool that can directly measure formation permeability downhole. Instead, it is to be estimated from tool responses, empirical relationships, or from derived core samples. Many of the empirical relationships that have been derived are specific to geographical and geological areas and may not be fully applicable to other areas. As such, it is common practice to derive a relationship between core porosity and core permeability, and then apply that relationship to the log-derived porosity. Core data is not always available and may only be present within a handful of wells within a field or development, and this is due to coring operations being expensive and time-consuming. As such, multiple authors have employed machine learning models that have been trained on key wells and then used to predict permeability in all other wells. In this example here, we have three common logging measurements: gamma ray, neutron porosity, and bulk density. And these have been used to predict core permeability using a novel method known as domain transfer analysis. The areas highlighted in track 2 indicate the data that was used to train the model, and the unhighlighted areas are where the model was used for prediction. The model has done an excellent job in the high permeability intervals, as well as capturing most of the variability within the lower permeability intervals. The models could be improved by adding more data or taking in multiple wells if they are available. Understanding the subsurface lithology is an important task in geoscience and petrophysics. Deriving a lithology flag or mineral volumes is one of the key tasks that is assigned to the petrophysicist. Machine learning algorithms have routinely been adopted to group well log measurements into distinct lithological groupings, known as Facies, and this process can be achieved using either supervised or unsupervised learning technique. Unsupervised clustering of data is a common form of exploratory data analysis, which is used to divide up the data into different groups based on the shared characteristics or properties. Data points that are similar to each other are grouped together in the same cluster, and those that are different are placed in another cluster. In this example here, we've used an unsupervised clustering technique known as k-means clustering, and this was done using data from a small selection of wells from the Force 2020 Norwegian competition dataset, and 4 standard logging curves were selected for model training here. As you can see in the results, a few of the clusters tie up nicely with the log responses, such as the light blue and the dark blue bars. Others are slightly harder to see on the log plot, and also on the density neutron crossplot to the right, especially at higher neutron porosities and lower density values. The final application we will look at is the prediction of petrophysical properties. This example here illustrates the results from the vol field that were used during this year's SPWLA conference workshop on machine learning. It utilises a clean dataset, one that has been QC'd and outliers have been removed. We have used this data to predict water saturation and porosity from standard logging curves. The data was split into 70% for training and the remaining data was used for validation. Once the model was validated, it was then used to predict onto a blind well, and these are the results of that prediction. We can see here that the prediction has done a very good job. However, there are some differences in the predicted water saturation, such as the lower interval where the interpreted data has been clipped to 1, yet the machine learning algorithm has predicted greater than 100% water saturation. So to summarise, the popularity of machine learning within our domain is greatly increasing and can have many powerful benefits and a wide range of applications to our petrophysical workflows. It can help speed them up, but machine learning should not be seen as a direct replacement for the petrophysicist. It should be seen as an additional tool in our toolbox if used correctly. Applications include missing data repair, Facies analysis, reservoir rock typing, depth shifting, log normalisation, and much more. And we can use machine learning to predict continuous data as well as categorically or discretely labelled data. As you can see, machine learning can be a very powerful tool. If you have any questions, please leave them down in the comments below. Thanks for listening, and until next time, bye for now.